You are given an array of numbers, and you need to find the longest stretch at the very beginning that counts up one by one like 3, 4, 5. Add up that stretch of numbers to get a starting point, then find the smallest number that's missing from the array but is at least as big as that sum, and return it. Say these are coupon codes, sorted 1, 2, 3, 6, 10. You would expect 1, 2, 3, 4, but it jumps straight from 3 to 6. The question, what's the next safe number to hand out? Hey, I'm Kai, and this is Fun with Learning Technology, where we take one problem a day and actually understand it, not just memorize it. Today is rated easy, but it hides a real edge case people miss. By the end, you'll spot this exact pattern in seconds. Here's the deal. We are given a list of numbers. We find the longest run at the start that goes up by exactly 1 each step, sum it, then return the smallest number missing from the array that's at least that sum. This looks like it might need something fancy. Sorting, a heap, dynamic programming. It doesn't. One pass through the array with a running sum solves the whole thing. Clean. This exact shape shows up anywhere numbers get handed out in order. Database IDs, invoice numbers, ticket systems. Get the edge case wrong here and you silently reuse or skip a number in production. Take 1, 2, 3, 2, 5. The prefix 1, 2, 3 climbs by exactly 1 each step. It sums to 6. 6 isn't in the array, so 6 is our answer. We only need 3 things. A running sum we build as we go, a plain loop that tracks position, and a check for whether a candidate number already exists in the array. First instinct, just take the biggest number and add 1. But that ignores the gap entirely. 4 and 5 are still unused. Instead, look at how far the array stays perfectly sequential from the start. 1, 2, 3, each one is exactly 1 more than the last. Then 6 breaks the chain, since it's not 4. As we walk the sequential part, we keep a running sum 1, then 1 plus 2 is 3, then 3 plus 3 is 6. That running sum is our candidate answer once the streak breaks. Why the sum and not just index plus 1? Because we need a number bigger than everything already claimed in that run. Sum plus 1 guarantees that. Sum is 6, so the candidate is 7. Now check, does 7 exist in the array? It doesn't. 6, 10, so 7 is missing. That's our answer. Now flip it. Array is 3, 4, 5. It is sequential, but it doesn't start at 1. So 1 itself was never claimed. The answer is just 1. No summing needed. So the plan, walk the array building a running sum, stop the instant the streak breaks. If the very first number isn't 1, we already know the answer is 1, no loop needed. We start our total at the very first number, then walk forward. Each time the current number is exactly 1 more than the last, we add it in. The moment that fails, we stop. If the array doesn't even start at 1, we return 1 immediately. That's the trap case. Otherwise, we start checking from total plus 1 and keep bumping up until we find a number that's actually missing. Here's the whole thing together. Walk the sequential prefix, sum it, then search upward from sum plus 1 for the first missing value. Let's trace 3, 4, 5, 1, 12, 14, 13. The streak is 3, 4, 5, total becomes 12. Since nums at 0 is 3, not 1, our sum only matters as a floor. Candidate starts at 12. 12's in the array, 13's in, 14's in, 15 is missing. Answer 15. Let's trace 1, 3, 5. The streak check fails right away since 3 isn't 1 plus 1, so total stays at 1. Nums at 0 is 1, so no trap here. Candidate becomes 2 and 2 isn't in the array, so 2 is our answer. Nums at 0 is 2, not 1. So the trap case fires right away and we return 1. The loop never even needed to check the streak. The realistic mistake here is skipping the check on whether the array even starts at 1. You sum the streak fine, but if it starts above 1, sum plus 1 is wrong. Always check nums at 0 first. An alternative is converting the whole array to a set up front, so membership checks are instant. It works, but for arrays this small, it's extra memory for a lookup. You're barely doing more than a few times. Time is big O of n. We touch each number a small constant number of times. Space is big O of 1 beyond the input. We're not building anything extra. A single number array just uses that number as the streak. An array starting above 1 hits our trap case. And a fully sequential array still correctly searches upward from the sum. So, walk the sequential streak, sum it as you go. If nums at 0 isn't 1, the answer is just 1. Otherwise, the answer is that sum plus 1, the smallest number the streak never claimed. Remember the 3, 4, 5 trap from earlier? Now you see exactly why it needed its own check. New daily drops tomorrow, same time. This channel grows one like and one subscribe at a time. Yours would help. If something feels off or missing, or you want to see something new, tell me in the comments. Quick one for you. If the array is sorted, no dupes, and the running sum never breaks the streak, what do you return? Pause and think it through. Take a second before I give it away. You return the total sum of the array. The streak held all the way through, so the sum itself is the smallest missing integer. Round 2. Why do we track the running sum instead of just index plus 1? And once a duplicate or gap shows up, what's the answer? Guess before I answer. Give it a beat. Index plus 1 breaks the moment there's a duplicate, because the index drifts from the value. The running sum stays honest, so the answer is just the sum right where the streak stops.